4.75 moles of 3 even 0.75 moles of hydrogen. Now we're almost there. I've made this up, so I'm not going to do it. But what you would then do is you'd say, okay, moles over volume gives you the concentration, yes? And obviously that's assuming that the volume is in decimeters cubed, but anyway. Moles over volume gives you the concentration. Moles over volume gives you concentration. Moles over volume gives you the concentration. You plug them in. What do you do with this one? Well, that is going to be 1.5 over T squared, of course. This is going to be, etc., etc. Do you all get it? Yeah. Yeah. So you put those in, and then you calculate Kc. Okay. And that's a typical equilibrium question. Any questions? Okay. Now, that is pretty much it for equilibrium. It's practice, apart from that. There's a little bit about phase equilibrium, but we'll do that at the end if we've got time. Move down. Okay, now pH. Now all pHs, now we're moving on to acids and bases. Okay. And what I'm not going to do again is I'm not going to go through all of the very simple acids and bases stuff. I'm not going to, you need to look in your revision books, you'll find there are two theories of acids and bases. One is Bronsted-Lowry, which is proton donor, proton acceptor. The other is Lewis acids and bases, which is electron pair donor, electron pair acceptor, except it's the other way around. So for Bronsted-Lowry, an acid is a proton donor. For a Lewis acid is an electron pair acceptor. But just look it up and it's fairly straightforward. Okay? The other thing I'm not going to go through is all the stuff about weak acids and strong acids and pH scale, in the sense that, you know, I'm not going to tell you that the pH of 5 is orange in universal indicator. What? What's wrong?
He's asking what the case is.
So, let's start with some of the maths, because now we get on to the point where people start to get a bit worried. But you mustn't worry, because it's actually not that complicated. pH is equal to minus log to the base 10 of the concentration of H plus ions. That's what pH is. Now, hang on. What's wrong? What's wrong? Come on, because you're not listening now to what's wrong.
That's fine. We're actually just talking about... Well, where you got 2.25 from, we didn't know. It's because you divide, you times the 0.75 by 3. Yeah. And minus it.
It's because if you can times 0.75 by 3. It doesn't matter how you get it. But the point is that the key thing is the reacting quantities, isn't it? That's what I mean here. That if 0.75 moles of this is reacted, then it's going to be 3 times the amount of hydrogen which will react. Yeah? So these are the giveaways, these coefficients. Do you remember at GCSE you spent so much time learning how to balance equations? Well, that's why it's so important. Because those are what you use in all your calculations. Okay. Right. pH equals minus log to the base 10 of hydrogen ion concentration. Okay. Now, what that means is that pH is a logarithmic scale. Okay. So once you get the hang of this, it's very simple. Why do we make pH a logarithmic scale? Well, the answer is because it's much easier to handle. Okay. So the concentration here, what's the pH if that's the concentration of H plus ions? 4.
3 or 4?
Well, let's go through it. If the concentration of H plus ions is 1, what's the pH?
0, yeah.
10
to minus 3.
Okay. Hang on. Let's look. So, log of 1 is 0. Okay. It doesn't matter if I make it minus. Log of 1 is 0. So concentration H plus ions 1, pH is 0. So if it's 0.1, the pH is 1. Yes? Okay. Now, of course, the log to the base 10 of 0.1 is minus 1. but the minus makes it a positive scale. So the minus is just there to make it a positive scale, and the fact that it's logarithmic is just to make the numbers integer values. Okay, so here we go. 2, 3, etc., etc. Yeah. So we're always dealing with very low concentrations of H plus ions, really. And so that's why we've made this minus, because then we get a positive scale. And that's how pH works. Now it's an interesting one, because we now have to introduce another idea, and that is Ka. I want you to be aware of what Ka is. Well, Ka is, if you take an acid, Ka is called the acid dissociation constant, and an acid in water is dissociated into its constituent ions, isn't it? Yes? Now this is an abbreviation, by the way, because H plus, a proton, imagine a proton without anything else, just a proton floating around in solution. Well, it doesn't happen. This is actually an abbreviation, because what happens is an acid will react with water and it will produce H3O plus A minus. And so whenever you see H plus, actually it's an abbreviation of this, which is H3O plus. Please don't talk while I'm talking, it's really disruptive. Oops. But what we do is, we don't bother putting all this in chemistry because we like to have abbreviations, of course. So what we do is we just take out the water. And what Ka, by the way, is found from Kc. So this would be my Kc, wouldn't it? Concentration, there it is, Ha over H2O. And what we do is we say concentration of water is a constant. It's 55.5. It's easy to work out, because all you do is you say, right, hang on, if you've got 1,000 grams of water in 1 decimeter cubed, incidentally, 1,000 grams of water in 1 decimeter cubed of water, you can work out how many moles that is, divide that by 18, it's 55.5, so it's 55.5 moles per decimeter cubed. So that's the concentration of water. You take the concentration of water, you multiply it by Kc here for this, and you end up with the value for Ka, which is effectively the concentration of H plus, isn't it? Which we've abbreviated. H3O plus is our abbreviation. Sorry, H plus is our abbreviation of H3O plus, divided by concentration of HA. Okay. Now don't worry too much about where all this comes from, because you'd never be asked that in an exam, but it does help, I think, to understand a little bit more about where this comes from. But what is this? Well, all this is a measure of, hang on a minute, it's called the acid dissociation constant. So it's a measure of how much an acid dissociates. Can you see why? Yes, of course you can. Because if the concentration here of HA is very low, and these are very high, then Ka will be very big. Yes? So if Ka is big, it means that you've got lots of ions and not very much undissociated acid, which means it dissociates a lot. Yes? On the other hand, if it's the other way around and you've got a very big number here, you're going to have a small fraction. And so Ka is going to be very small, and that tells you it doesn't dissociate very much at all. Okay. And this, of course, now casts a completely different light on pH. Because, aha, you cry. You probably cried in your lessons when you learnt about it, but I'm just reminding you. Aha, you cry. pH is not a measure of acid strength. Is it? No. pH is not a measure of acid strength, and it's interesting because we regard it as a measure of acid strength at GCSE, but it's not. Because what is the definition of a strong acid? An acid which fully dissociates in solution. So make a note of that. A strong acid is an acid that fully dissociates into solution. A strong base is a base that fully dissociates in solution. And when I say fully dissociates, of course, I mean splits up into ions, don't I, guys? Yes, splendid. And a weak acid or a weak base a weak acid is an acid which does, or that only partially dissociates into ions in solution. Now, can you see why pH is not really a measure of acid strength, but Ka is a measure of acid strength? Because we've just said that our definition of an acid is how much it dissociates. Well, this measures directly how strong an acid is. Because if Ka is big, it means it dissociates a lot. Okay? But, of course, this just measures the concentration of H plus ions. Now, if you have a strong acid, if I take some sulfuric acid,